feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines. As we continue in Unit 6, in Unit 6 we have been looking at radicals, radical expressions, and now on to radical functions. So today we are going to take a look at radical functions and their graphs. First, let's go ahead and define a radical function. So a radical function is any function defined by a radical expression. Breaking down that name kind of makes sense. So we've been dealing with radical expressions, and I have an example of what a radical expression may be. So f of x would be a radical function if it is equal to the nth root of a to the n power. Remember, this can also be written in rational exponent form, where the index or the power of the root is the denominator of the exponent, and the power of the radicand is the numerator of the exponent. So both of these would be considered radical or root functions. We are going to start here today by taking a look at their graphs. So let's go ahead and graph the square root of x. I'm going to show you how to graph it in your graphing calculator, but also show you how to quickly graph it by hand. A square root function, what a square root function does is square roots the x value. So basically, if we're going to graph this just how it is, we want to look for x values that can be square rooted. So the square root of 0, 0 has a square root, it's 0. The square root of 1 would be 1. The square root of 4 would be 2. The square root of 9 would be 3, and so on and so forth. So these would be the points that fit on our graph. Notice that it only goes here to the right. Remember, I cannot square root negative numbers unless I use imaginary units. So yes, the square root of negative 1 is I, but that's actually not going to show up on the graph because imaginary units aren't part of the Cartesian plane. So here's our graph for the square root of x. Now we can also use the graphing calculator for this. If I go to y equals and clear out what's in there, I can type in the square root of x, and I can go ahead and take a look at my calculator, and we see basically the function that we have listed here. If I looked at the table, I can see those square roots that match up. So the square root of 1 is 1, square root of 4 is 2. I could go down and see the square root of 9 would be 3, and so on and so forth. So here we have the graph of f of x. The question also said we wanted to list domain and range. So remember, the domain are the x values of a function. So the domain of this function would be any x value starting at 0 and including 0 going to the right forever. So the domain would be x is greater than or equal to 0. The range would actually be the same on the y's. So the range are the y values that are included in the function. And in this case, we start at the lowest y value of 0, and we go up forever as we go off to the right. So the range would be also y is greater than or equal to 0. Now, let's take a look at number 1b here. G of x now is the same square root function, but what we've done is we have actually added in some transformations here. So you guys may recognize this as transformations on the square root function of x, which would be a shift right 2 here and up 5. So if I take my origination point that's at 0, 0, and I shift right 2 and up 5, there's my new point. From here, I could look for numbers that could be square rooted. So if I go 1 over from my origination point, the square root of 1 is 1. I would move up 1. If I go over 4 units from this origination point, so I start here and I go over 1, 2, 3, 4, the square root of 4 is 2. There's my next point. My next point for this graph would actually be off of our coordinate plane here. I would have to go over 9 units to 11 and square root 9, which would be up 3. So this one would actually be off the graph. You don't really need to include that if you don't want to. If I check this with my calculator, the square root of x minus 2 would be inside the square root, plus 5 would be outside the square root. I can take a look at this graph, and it looks pretty similar to what we have here. Checking the table, I would see a point at 2, 5 that we have. I would see a point at 3, 6 that we have. And we could continue to get 6, 7, and other points. So here's our graph. Notice on the table there, it does say error at x equals 0. X equals 1. X equals 1 does not actually have a value for this function. It did on the previous one, but now that we've shifted the function, it's changed our domain and our range. So now my domain for the function would be starting at 2 and going to the right. The range for the function would be starting at 5 and going up. So we can see the shifts left to right and the shift up and down starts to change the domain and the range for the square root function. Now let's take a look at some more types of graphs for root functions. Let's look at a cubed root. So in 1c, we have h of x that is the cubed root of x. So again, I'm going to quickly do this by hand. Now I'm looking for numbers that I can cube root. So the cubed root of 0 would be 0. The cubed root of 1 would be 1. The next number I could cube root would be 8. The cubed root of 8 would be 2. And then the next number that you could cube root would be 27. So that would be well off our graph. I can also go the other direction here from our vertex or origination point at 0, 0. The cubed root of -1 is -1. Remember, we can cube root negative numbers. So the cubed root of -8 would be -2. So we can type this function also into the calculator. To find the cubed root button, you can hit math and go down to this fourth option, which is the cubed root of x. And I can take a look at this graph. And I can see a shape that somewhat resembles what we have here. So it's going to be almost the same as a square root going to the right, a little bit different rate of change, but it's going to go to the left as well. So there we have our cubed root function. You could check the table here and identify that we have some of the correct points. The points here that we have on our graph are also part of the function. The domain and range for this is going to be slightly different. The domain is going to be any x that is greater than, the domain is going to be any real number. So it goes to the left forever, and it goes to the right forever, so the domain is going to reach all real numbers. The range is also going to be all real numbers. So though it doesn't move up or down very quickly as we start to stretch out to the right and to the left, it is still going up and down, and so it's going to hit all real numbers. Let's go ahead and take a look at the fourth root. So in our calculator, I'm going to go ahead and fourth roots are a little bit more challenging to probably figure out for us. So let's just go ahead and graph this. If I want the fourth root, I'm going to type in under y equals, I'm going to type in first 4. Then I'm going to hit math and go down to the fifth option, which has the xth root. So it puts that 4 up there in the index. And I'm going to take a graph of this. So if I look at the table here, I am going to have a point at 0, 0. I am going to have a point at 1, 1. My next point that we would graph would not come until 16. So this graph is going to not even get to the 2 here on our plane. Draw it a little bit more accurate. It's going to look something like that. It's slightly going up as we go to the right. Looks similar to the square root graph. But has a much lower average rate of change as we go from left to right. The domain for this is going to be similar to what we saw with the square root. So the domain is going to be x is greater than or equal to 0. And the range is going to be x is greater than or equal to 0. Y is greater than or equal to 0. Now, let's take a look at some other ones. Let's look at maybe the fifth root. So what we may notice here is that the fifth root, when I graph it, looks very similar to the cubed root. But again, the rate of change is going to be slightly different. So if I were to draw a fifth root, it would pass through 0, 0. It would pass through 1, 1. But then its rate of change would be slightly different as we move to the left and as we move to the right. would look something more like this. Okay, so what we're going to notice is that roots with an odd index are going to have some very similar properties. Roots with even index are also going to have very similar properties. The domain and range for roots with odd indexes is going to be all real numbers. The domain and range for roots with even indexes are going to have some kind of relationship where it is greater than or equal to a number. So let's actually take a little bit closer look at domain and range. So in problem number 2, it says without the use of technology. So we're going to try to find the domain and range first, and then maybe check the graph. So the domain and range for an even indexed function, so a function with an even index, this would be a square root, which would be an even index, is going to have some restrictions on it. So let's first start with the domain, and we'll do this algebraically. A function, if you think about a square root, if you will, we know that when graphing, we're dealing with the Cartesian plane, or real numbers. So we know that with a square root, you cannot have a negative inside of the root, or else you're dealing with imaginary numbers. So essentially what we can do algebraically is we can look at this as kind of a shift to the right 4, but we could also look at this as x minus 4. That expression has to be greater than or equal to 0. This allows us to quickly find the domain. Add 4 to both sides. So the domain is going to be x is greater than or equal to 4. The range is going to be a little bit more challenging. There's not really a set way that we necessarily can come up with the range. Not quite as easy algebraically. Essentially what we can do for range is take a look at the transformations. So without transformations, the range will always be greater than or equal to 0. However, we notice that here there is a vertical reflection. So how does a vertical reflection affect the range? Instead of being greater than or equal to 0, it's going to be less than or equal to 0. So essentially we can start with the range. We can start with y is equal to, we can start with y is greater than or equal to 0. And then apply transformations. For the domain, we can set the radicand greater than or equal to 0. Now this is going to work with functions with an even powered index. So if we check this, we can type in that function. So negative square root of x minus 4, let's try that again. Negative square root of x minus 4. Take a look at the graph here. I can see that the domain is anything including 4 and going to the right, and anything for the range including 0 and going down. Now for roots with an odd powered index, it's a little bit easier. Domain and range will always be all real numbers, or for all cases that we will see in Algebra 2. So because this function always, because a cubed root or a fourth root or fifth root, etc., can root both positive and negative numbers on the x-axis, it will stretch forever to the right and to the left, and it will go up and down forever. So we could check this with any cubed root that we want. So we already took a look at one example of a cubed root prior to this problem. I can type in this cubed root. So the cubed root of negative x plus 6 minus 2. It's going to look different than the graph that we did before. It's going to have some translations on it, but it's still going to go to the right and to the left forever. It's still going to go up and down forever. So our domain and our range is going to be all real numbers. At this point, see if you can pause the video and find the domain and range for h of x. Hopefully you got a chance to find the domain and range for h of x. Let's go ahead and take a look at it. So the domain would be any expression that is greater than or equal to the radicand. So we would subtract 3 from both sides to get 2x is greater than or equal to negative 3, and then divide by 2 to get x is greater than or equal to negative 3 halves. For the range, we could start with our vertical we can start with y is greater than or equal to 0, and then we can apply translations or transformations here, vertical transformations. So this is a shift down 8, so the range is going to end up being y is greater than or equal to negative 8. Now let's go ahead and graph this to take a look. So y equals, let's clear out that, type in my 4, hit the math key, the 5th option down, and type in 2x plus 3 minus 8, and take a look at that graph. And so we can see that negative 8 is as low as it gets on the y, and here it's not easy to see here, but it is directly in between 1 and 1/2. You could look on the table there, go back to negative 8. Quickly do that. Sorry, it's on the x-axis, so we'd have to stop. I'm not going to mess with the table. We can do second trace value because we believe it's negative 3 halves. Type in negative 3 halves, and the y should be negative 8, and it is. So as far as we get to the left is negative 3 halves or negative 1/2. So this is kind of a quick overview of graphs and domain and range of root or radical functions. All of these concepts that we discussed here in this video will carry over to any type of transformation on the root functions that we're going to see in Algebra 2. As always, guys, thank you for tuning in, and we'll see you soon.